Vamos a comenzar entonces con la última presentación de este bloque de Data Science para reservorios. Les recordamos nuevamente que van a tener sus micrófonos y cámaras apagadas durante la presentación, así que todas las preguntas que les surjan durante la misma las deben canalizar a través de el panel de preguntas y respuestas con las letras P y R en el margen inferior derecho de la pantalla de la WebEx. Dicho esto, ahora sí le vamos a dar la palabra a los disertantes de este trabajo titulado Automatic Filling of Gaps in Well-Load Data, a Data Science Approach. Los autores son Sergio Velasquez y Szymon Ligeza de Hamilton. Sergio, bienvenido y adelante entonces con la presentación.
Ok, muchísimas gracias, Adrián. Voy aquí a compartir. Ok, déjame hacer aquí un pequeño cambio respecto a esto para que podamos... Ok, creo que ahora sí ven mejor, ¿cierto?
Está viendo el panel lateral, tiene que ir a Display Setting y quitar el display lateral.
Ok, entonces déjame mirar. Ahora sí, ¿no?
Correcto.
Ok, ¿estamos en break o iniciamos de inmediato?
No, el tiempo está corriendo.
Ok. Ok. Okay. Today, this presentation is going to be in English. I'm here with my coworker, Szymon Ligeza. Let me introduce Szymon. Szymon is a data scientist. He is right now working for Europe region. And myself, I'm Sergio Velasquez. I'm reservoir and production consultant for Latin America. Okay, so today we're going to be showing this approach, this solution, which is the automatic filling of gaps in well-logged data using data science. Let's start with the challenge. Okay, so as many of you know, LWD and wireline has been one of the most popular techniques for acquiring data of the subsurface. But in some cases, these are very complex operations, and excessive penetration rates and high cable write speeds in the case of wireline, or poor return signals between others in some cases lead to some gaps in the well-logged data. So for many years, we have been performing interpolation to fill these gaps, but interpolation only works for small gaps in the data set. Okay, so we need to find a good way to solve this problem, and machine learning is a very good approach for this. So let us show how we solve this. In this case, we had the data available was 2 wells. We had 2 wells. We had 4 last files to do it, and we had 97 different logs and also 34 common logs. Why is it important? The common logs are very important because we need to focus on those logs that exist in all the last files. Okay, so this is the data that we have, and what was the pipeline? So basically data input. So we try to use as many last files as we have just to make a robust model. And the first step, and I think it's one of the most important steps, instead I think it's the most important step, is on anomalies and outliers detection, especially when we are dealing with log data, with petrophysics data, because it's very sensitive. Then we perform a data imputation process to obtain a very complete data set for training machine learning algorithm. And finally, we perform the prediction based on the model. Now you will see what's the workflow and what's the model that we are using. Okay, so data input. As I told you, we have some interest last file. Let's imagine you have a last file or well-logged data file where you have some gaps, very large gaps actually, and you want to fill it. So you can select, or you can include many last files from different basins, from different wells, to work as trainers for the model that you will use in your interest well. So this allows you to include behaviors from different subsurface environments and different basins. Okay, so every data set must contain the interest log to be predicted. The columns from the other files will be used as features, and these complementary data sets, those from here, will improve your prediction. Okay? So once you understand the data input, you go to outliers and anomalies. As I told you, I think this is the most critical step because this data is very sensitive, it's very spiky. You have a lot of peaks. So we developed a 3-step methodology to identify anomalies and outliers. The first one was quantiles to remove very remarkable outliers. The second one is rolling window using z-score, and finally dimensionality reduction. As you can see here, we use quantiles to remove the 0.1% of the data, which is actually, it won't affect the training of the algorithm in terms of amount of data, but we will be able to remove those data points that are very high or very low. Then we use rolling window with the z-score to perform a slightly smoothing of the data. We are removing the spikes, and then we do a dimensionality reduction. Szymon, I don't know if you want to add something here regarding the dimensionality reduction.
Yes, thank you, Sergio. So I will continue. I will tell something about this dimensionality reduction technique. So if we have already cleaned data with very remarkable spikes which can affect prediction, we can go to the next step, which is outliers, anomalies detection. And we can do it by applying principal component analysis algorithm to reduce those big amount of dimensions to, let's say, only 3 dimensions or even 2 dimensions. Why it's matter? Because in reduced dimensionality, first we can plot it. Yeah, so everybody would like to see the data, how it looks like in the space. So that's some advantage, and we can see that here in the 3D plot after dimensionality reduction, we've got 2 spots of data. So if we retrieve the original dimensionality, we can then compare to the original data. And if after retrieving, after inversing, if the error between the original data and data which we retrieved is huge, that means that this is probably anomaly. So setting threshold, we can we can remove all anomalies, all data which are above the threshold which is above a reconstruction error. It's so-called reconstruction error. So we set reconstruction error. If something is above this reconstruction error, that means that probably we don't want to use this. and we were able to detect those outliers, and even step further here into the dimensions. We are presenting two clusters, which actually on the yellow one represents well-logged data which was collected accidentally in casing parts of the well. So we don't want them. Actually, this ranges where the casing part starts could be obtained from reports, and we did it. But actually, thanks to this techniques, we were able to see that there was a little overlap and in this casing part. So it affects training of the model and later on, because those data belongs to have completely different characteristics. So we have to detect them, we have to remove them. So as Sergio mentioned, the cleansing of the data here is a very important thing, and each file has to be cleaned perfectly. Sergio, would you like to continue?
Yep. Yeah, sure. Thanks, Szymon. So, well, here you can see that that part of the data was measured inside the casing, so it's very weird. So we automatically detected and we automatically removed it. So then we get a very a clean portion of the data. But now there is an important step right now. Okay, now you have that data set without that casing part, which belongs to open hole logs measured inside the casing. But now, for sure, you have those small gaps. And as I told you before, the interpolation and some other techniques have been used widely to fill these gaps, but not for large gaps. So we also perform some kind of techniques to fill these small gaps in order to get as more as data as possible to train the model for the large gaps. So how do you do that? You drop the original small gaps to obtain a fully complete data set. Once you have that, you can create synthetic gaps, small gaps. And you do it randomly, but as you are doing it randomly and those gaps are synthetic, you know what's the real value that belongs to that row. So you test different algorithms for filling those small synthetic gaps, and then you select the best one. In this case, the KNN with 5 clusters was the best option. So we use that algorithm to fill those original small gaps. So now that you have filled those those originally small gaps, you are ready for training your algorithm to fill the large gaps, which is that portion of the log where the interpolation is not that good. So how is the prediction approach? We classified the logs into several groups, let's say density, resistivity, gamma ray, and so on. And let's say you want to predict the sonic. When you do that, for example, you have 3 logs in the sonic group for that, for interest, last file or your log file. So you start to predict one by one using all the features that you have in the last files. But you do it one by one automatically. So the first log is predicted, and then the other one, and the other one, and so on. So you are getting as many models as files that you have loaded. Why? Because at the end of the day, you will combine those models into an ensemble learning technique, and you will see it right now. So here is the explanation of the ensemble learning. So Szymon, do you want to clarify this?
Yes. So I just mentioned that as on the previous slide, the distribution of the gaps really matters. If the gaps are, as you call them, small, if they are randomly distributed, there is not such a problem. That's why we would like to preserve as much data as we can. So if they are randomly distributed, there's not a problem to extract information from other columns, from other features, because those gaps doesn't correlate in the same ranges in several columns. The problem starts when we've got huge ranges of gaps in the same ranges in several columns. That's why we had to apply this kind of algorithm. And the point is to catch as many relevant data as we can from all possible sources, all possible files which we have. So if we train those models, this technique is very famous. Actually, the random forests are based more or less on the similar techniques. But here we the framework works in that way that extract as many columns as possible from each last file, trains the model, and is trying to predict our y hat based on data taken from this last file. Yes, the problem is
5 minutes left.
Okay.
Yes, the problem starts when all those files contain different types of different data, which can have completely different characteristics. They can the characteristic, I mean, they can be collected from using other equipment, so characteristic will be different. They can be taken from other wells, characteristic will be different. They can be collected in different times. So actually the problem is, which appears here is so-called covariate shift. And what about Sergio? Could you please another slide?
Yeah, sure. But before going to another slide, let me just clarify this idea. We have different tools acquiring the data in the subsurface, different companies measuring the data, different tools, different environments. So it means that there can be some bias. So the final objective of applying ensemble learning is to lowering the error and reducing the bias of these data sets. So, and the final objective is to minimize the mean square error of this. So the ensemble learning or model is basically a model that learns how to best combine different machine learning algorithms to create a prediction as close as possible to the original or to the expected prediction objective. Okay, Szymon.
So here's a general pipeline, which we actually already explained the workflow. So first, the algorithm, the framework is looking for the data which we would like to predict in other last files. Takes different last files to train several models. Then each of those models is trying to predict the value, but of course it was trained on different data, so the characteristic of the data will be completely different. So all those models usually are wrong. They are very weak. But here is the scale effect. If there's a lot of models, after averaging their decision, after majority voting, finally they end up with solution with results with calculation which are quite close to the ground truth. we will show you in other slide the problem about covariate the domain shift and covariate variance. So here we can see that each model is far away from the good decision. This is the result before applying adaptation and the normalization techniques. So actually, if we zoom it, we can see that the fluctuations are predicted correctly. The problem is with this shift. So after adaptation techniques and after applying averaging, we can see that if they vote together, if they cooperate together, they are able to predict very good the values which are very close to the ground truth.
Yeah, Szymon. As you can see here, we have these rows or red lines are individual models, okay, individual predictions. As you can see, it's very, not very, but it's far away from the real value, which is green. Then when you combine them, you obtain the blue line, which is capturing the trends of the real value, but you still need to perform some normalization techniques or adaptation process to reduce that correlation. And then when you do that, you obtain this the real prediction. Then you can take solutions up to 99% of R squared.
Excuse me, end of presentation block.
Yeah.
Start by question blocks.
Yeah, this is the conclusion.
Close. Okay.
Okay, the conclusion. So for the best cases, we obtained predictions of R squared up to 99%. As I mentioned in the beginning of the presentation, the data cleaning is the most critical step. In fact, I think once we could create that three steps methodology for cleaning the data, everything was much easier. The ensemble learning was observed as the best approach for the prediction because the merging of individual models reduced a lot the covariance, and also the normalization helped us to achieve the real value. And at the end, basically, the data interpretation using interpolation is still a very good idea, but it only applies for small gaps. So when you need to fill large gaps, the machine learning techniques helps a lot. So that's the presentation. Thank you so much for your time, and let us know if you have additional questions.
Okay. Thank you for your presentation. Well, there is not much questions here. Luis Navarro Morales only say that it's a fascinating presentation, and thank you very much for this. Okay. Victor Mendez asks if does this model work with real-time data or historical data?
It's historical data, actually. We are receiving the data, the last files, which is the output file from logging operation, and then we combine them together to create the model. If you collect files, last files from different basins, you are being able to capture different data behaviors in the subsurface from the different basins. So your model will be very robust. But that's not real-time data.
Actually, it could be, of course, extended to predict real data, because we were able to even extract whole column, whole feature, whole last column of one feature. So actually, that means that it would be actually possible to do this on the real data, but we haven't tested yet.
Okay. Okay, well, I think it's all we have here. Thank you again, Szymon, Sergio.